Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and we would also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and today we have got an ambitious task on our hands to relate together two very important concepts from macroeconomics and econometrics respectively. So let's start with the macroeconomics one first. We are going to investigate the Phillips curve, a very famous inverse relationship between inflation and unemployment in macroeconomics data. This relationship has been first discovered in the late 1950s by a statistician by the surname of Phillips, hence the Phillips curve. And it shows that the higher the inflation, the lower the unemployment, and vice versa. And this finding has been so influential that it has inspired generations of macroeconomic researchers and policymakers. And it's very easy to understand why is it so, because if the Phillips curve holds, then a policy authority, for example, a central bank, can choose an optimal trade-off between inflation and unemployment that would be the best for the society at large. However, there has been notable criticism directed at the Phillips curve, at least since the 1970s, that was showing that maybe the Phillips curve relationship has broken down since the late 1950s when it has been first examined, and it is no longer a reliable tool to inform public policy. Maybe it has never even existed, and it was just an artifact of statistical data mining. And maybe it has broken down at some point during those years, some point during the 20th century. Why might it have been the case? Is this simplistic inverse relationship between inflation and employment still relevant in 2020? Well, to answer this question, this is where our econometrics part kicks in. We're going to apply the Chow structural shift or Chow structural break test to determine whether the relationship has changed throughout our sample period, and if it did, what is the most plausible point in time when it happened. The Chow structural break test is very intuitive and very simple to implement. It involves estimating a regression on the full sample and on subsamples that are determined by applying some cutoff point. And by selecting this cutoff point, you can see whether a model that is estimated separately on subsamples has better explanatory power, explains more of the variance of the dependent variable, and leaves less variance unexplained. So to help us understand the Phillips curve and the Chow structural break test, we have got macroeconomic data on unemployment and inflation rates for the United Kingdom starting from 1855 all the way until 2016. This dataset comes from the project called A Millennium of Macroeconomic Data, and it's quite a nice historical touch, given that Phillips himself has first discovered this relationship on the UK macroeconomic aggregates. So, to start with, we have to estimate the Phillips curve, so the linear relationship between inflation and unemployment, on the full sample. So here we've got the template, and we just need to apply the linus function, selecting the unemployment as the dependent variable and inflation as an explanatory variable. We need the constant here, and the constant is actually quite important because in some interpretations of the Phillips curve, it is referred to as the natural rate of unemployment. This is the rate of unemployment that is consistent with 0% inflation, and in some other theoretical frameworks, it is referred to as the NIRU, the rate of employment that doesn't accelerate inflation. NIRU is an abbreviation for non-accelerating inflation rate of unemployment. Quite bulky, I know, but that's what we stick with. And we also need the additional statistics to be reported, so we know the standard errors, the degrees of freedom, and most importantly, the explained squared sum, so the variance of the dependent variable that the model explains, and the residual squared sum, the unexplained variance of the dependent variable. Here the dependent variable is obviously unemployment. So we close the parentheses and enforce the linus function using Shift-Control-Enter, and we've got the template over here with the coefficient standard errors and other statistics that can be helpful later on. And most importantly, perhaps, we have got this graph appearing on the right-hand side. The blue graph shows the relationship between inflation and unemployment for the full sample, and we can see that this relationship is indeed inverse. The higher the inflation, the lower the unemployment, and vice versa. We can see that the graph does intersect the x-axis, representing unemployment, at around 5.7, and it is verified by this intercept, showing that the natural or non-inflation accelerating rate of unemployment is indeed around 5.7 for the full sample, and the slope is minus 0.15, meaning that 1 percentage point increase in inflation reduces unemployment by 15 basis points, by 0.15 percentage points. So it means that roughly a 7 percentage point increase in inflation is needed to reduce unemployment by 1 percentage point. To determine whether this relationship is significant, we need to apply formal t-tests to the coefficients of our linear regression, and here we can calculate the t-stats by dividing coefficients by the respective standard errors, and we do it mostly for the slope, but also for the intercept. The t-test for the intercept would help us determine whether the natural rate of unemployment is statistically different from zero, whether there would be statistically non-negligible unemployment if the inflation is zero, but most importantly we want to test whether the relationship is significant. And here we can already see that the magnitude of this t-stat is quite high. It's higher in magnitude than 2, a usual rule of thumb for statistical significance in t-tests, but to be rigorous we need to apply formal two-tailed t-test, inputting the absolute value of a t-stat and the number of the degrees of freedom given by the Linus template over here. And we get a p-value that is much lower than 1%, that's quite close to zero, meaning that the relationship between inflation and employment on the whole sample is indeed statistically significant and negative, just as Phillips himself suggested. And the intercept is also significant, meaning that there would be non-negligible natural rate of unemployment if the inflation rate is zero. And now we have to determine whether this relationship is the same throughout subsamples. And to do that, one can just select a plausible cutoff point when the relationship could have changed, could have broken down perhaps. And I have selected quite a natural and easy breakpoint, that is 1931, when Britain went off the gold standard. And this obviously changes a lot of monetary arrangements in the economy and could change the underlying macroeconomic laws that govern the economic development and could change the relationship between inflation and employment. So this is a plausible hypothesis to test. Did going off the gold standard change the relationship between inflation and employment? So what do we need to do now? We need to estimate the same linear regression on subsamples before the UK went off the gold standard and after it did. So first of all, we do it for the first subsample leading up to 1930, so it would be the gold standard subperiod. We need to apply Linus to unemployment as the dependent variable again, leading up to 1930, so until row 77, and inflation as well for the same time period. And we still need the constant to estimate what the natural rate of unemployment was in the gold standard period, and we need the additional statistics as well. And we enforce this formula using Shift-Control-Enter, and we get our statistical output, and we get our orange curve that represents the Phillips curve for the relationship between inflation and employment up to 1930 in the gold standard period. And we can see that the slope of the curve is quite a lot steeper. It means that 1 percentage point increase in inflation would reduce unemployment by 0.2 percentage points, quite a lot higher than here. It means that a 5 percentage point increase in inflation would reduce unemployment by 1%, not 7 as previously. And the natural rate of unemployment is a little bit lower than in the full sample. And we can see it from comparing these two figures, and we can also see it by using the intersection, the intercept point in the graphs of the x-axis. Also, we can apply the t-tests as well, copying these across for the new regression estimated on the gold standard subsample, and we see that the relationship was quite a lot more statistically significant back in the gold standard era. So here we might suggest that, well, was it the case that the Phillips curve was more relevant for the gold standard period and maybe less relevant after the UK went off the gold standard? To test that, we have to apply the linear regression for the second subsample from the 1931 until 2016, the period when the UK was no longer on the gold standard, when it did abandon it. So we need to enforce the Linus function starting from row 78, so representing year 1931, and until the very end of our sample period, here it's 2016. And do the same for inflation, our independent explanatory variable. And here we still need the constant for the natural rate of unemployment, see how it changed, if any, and we need to apply 1 here for additional statistics. And here we can enforce it using shift-control enter, and we get our regression output and the gray curve that represents the Phillips curve for the post-gold standard era. And we see something really interesting here. We can see that the slopes of both the orange and the gray curves are quite a lot steeper than the slope of the blue curve. And it's not something that you would expect it initially. Well, if the slope for first subsample is greater in magnitude than the slope for the full sample, you would perhaps have expected that the slope for the second subsample would be lower than here, perhaps much lower, perhaps even insignificant. But that's not really the case here, because if we apply t-tests, we can see that the significance, the statistical significance of the slope is still maintained, at least on a 5% level. And what did change significantly is the intercepts, the natural rates of unemployment. And we can see it even from the graph. We can see that the slope didn't change much, but the natural rate of unemployment in the post-gold standard era is quite a lot higher. It's between 6 and 7%, 6.4% to be precise. That can be looked up at the Linus template, than the one before the gold standard was abandoned, 5.1%. And the slope didn't really change. And that reflects heterogeneity biases. That is a very important issue with econometric estimations overall. When you estimate some econometric equation in the whole sample, you implicitly assume that the relationship remains the same throughout the period. If there is any relationship, it should be the same throughout. But if it's not, then the parameters that you estimate on the full sample can be biased. And that's one of the main applications of the Chow structural break test. It can lead you to select appropriate subsamples to estimate your econometric equations and to extract some information from the data you have. And here we already approach the main part of our tutorial. This is how to determine whether the changes in relationships, changes in the relationship between inflation and unemployment were significant in the gold standard period and in the post-gold standard period. Well, to do that, we have to apply the Chow structural break F statistic, which basically tells you how significantly does estimating a model of some samples increase the explanatory power of the model. And here is where the explained squared sums and the residual squared sums play a very important role. Here we need to see what is the unexplained variance, the residual squared sum, in the short model where we assume no structural shift, in the model that we estimate across the whole sample. So here it is in the Linus output, 1370. And also we need to see what is the residual squared sum, the total unexplained variance, in the long model that we estimate across two subsamples, gold standard and post-gold standard. And here we just need to add up those two residual squared sums from the two Linus templates for subsamples. And we can see that it's quite a bit lower, but that's no surprise. Well, if you include more parameters into your model, or you estimate your model on various subsamples, your total residual squared sum cannot increase. It can stay the same or be reduced. What the Chow structural break test allows to tell is whether this reduction in unexplained variance, and by extension the increase in explained variance in the explanatory power of the model, is statistically significant, is high enough for you to warrant this model estimation on subsamples. And by extension, in application to the Phillips curve, it would allow us to tell whether the Phillips curve law for the UK changed when it went off the gold standard. To apply the Chow F-test, we need first of all to know what is the number of observations, and to do it we can count any of our columns. So for example, counting the number of unemployment observations we've got 162 of them. Then we need to calculate the number of the degrees of freedom for the test, and as suggested by this formula, it's n-2k, where k is the number of parameters in our linear regressions. Well, it's just 2 because we've got the intercept, natural rate of unemployment, and the slope, so the magnitude of the relationship between inflation and employment. So we can go two ways, either as suggested by the formula, n-2k, so 162 minus 2 times 2, giving us 158, And you could also add up the degrees of freedom given by the two subsample regressions. So here is the degrees of freedom for the first regression for the gold standard period, and here's the degrees of freedom for the non-gold standard period. We can add them up and still get 158, so both methods are useful. And then we can calculate the f-stat finally. In the numerator, we have got our residual squared sum for the short model, for the model on the whole sample, minus the residual squared sum, the unexplained variance for the long model on two subsamples. And we need to divide it by the number of parameters we've got in our model, and this is 2, because it's just an intercept and slope. And in the denominator, we have got, again, the unexplained variance that is remaining, so sum of residual squared sum across the two models on subsamples, divided by the final number of the degrees of freedom in the long model, and it's 158. And we close the parentheses and can calculate our f-stat, which is around 4.3. To determine how significant this improvement in explanatory power is, we have to convert this f-stat into a p-value using a right-tailed f-distribution. Why right-tailed? Well, again, because our explanatory power cannot be reduced. It can stay the same or improve. And we want to see how significant this improvement is. So right-tailed f-distribution, inputting the f-stat as our x and inputting the degrees of freedom of the number of parameters, so 2, intercept and slope again, and the second degrees of freedom is the degrees of freedom of the final model, 158. And we enforce this formula and get a p-value of around 1.5%. This is significant at 5% and insignificant at 1%, suggesting that, well, to some extent, the relationship between inflation and employment did change following the abandonment of the gold standard. And this change mostly reflected not in the relationship between inflation and employment per se, because these slopes are quite similar, but in terms of the increase in the natural rate of unemployment following the abandonment of the gold standard, with it increasing around 1.3 percentage points from 5.1 to 6.4%. But is it the best way we could have estimated our Chow structural break test? Why did we select 1930 as the breakpoint? Why gold standard is particularly relevant for the relationship between inflation and employment? Could another breakpoint serve our purpose better? Maybe if we select another year, it could show us a more significant result. Well, here I apply exactly that. I estimate the Chow test for every single breakpoint year that could be possible in our sample period. So from 1958, that's the first candidate breakpoint year that we can estimate the model for. Well, because if we start at, for example, 1956, we haven't got enough data to estimate our linear regression, because we only would have two variables. Degrees of freedom 0 doesn't work. And ending up on 2014, which is, again, the last year that we can use given our data ends in 2016. And what is done over here is the subsample length is calculated given at which year do we calculate the breakpoint. So in 1958, our first subsample would only have 3 observations, and that's the minimum possible. And in 2014, our second subsample would have 3 observations, that's the minimum amount possible. And then what is done is we calculate residual squared sum for the first model and for the second model, and calculate our f-stats using the same procedure that I have outlined previously. If you would like to go deeper into this particular calculation, you could always see the spreadsheets on your own in our Google Drive, or just request it in the comments below and I can go deeper into this procedure, potentially in a spin-off video on this topic. But what is most important is we can see what breakpoint years give us the highest f-stats. We have got it in the graph over here. We can see that actually 1931 is not the best year that you could select, because there are even more significant spikes in f-stats throughout the sample period. Most notably, there are spikes in 1970s that probably correspond either to the stagflation episode that actually was very instrumental in the academic criticism of the Phillips curve. Phillips curve predicts that you cannot have very high inflation and very high unemployment at the same time, at least in the basic, simplistic elaboration of the Phillips curve. So maybe that's when it did break down. And we also have minor spikes after the First World War, so maybe something changed later on. But again, do you really need to do all of these voluminous calculations to get something like that and select an optimal break-off point? Turns out you don't really have to do it, and you can use a very clever way of estimating a Chow test with a multiple regression with dummy variables that I will cover in the next video. As for now, that's all there is for the classical interpretation of the Chow test and its application to the Phillips curve in the United Kingdom. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions on videos for business, economics, or finance you would like me to record. And don't forget to subscribe to our channel and consider supporting us on Patreon. Thank you very much, and stay tuned.